Have you ever wanted to make your own ChatGPT from scratch? I'm talking about from a completely empty nothing over to something. I'm not talking about fine-tuning. You've probably heard of ChatGPT, which is OpenAI's product that allows you to chat into a large language model and it will perform tasks for you. It'll actually do the things that you ask it to do, but it will do the things in like text responses, right? So it does a pretty good job from that perspective. Though, what if you wanted to make your own, or at least probably not as big as ChatGPT, but maybe something that's very custom? You can do that using FemtoGPT. GPT, of course, stands for Generative Pre-trained Transformer. Now that means that essentially it's an unsupervised learning model where you provide it a whole bunch of data and then text data, right? And then it will take that data and then it will learn how that data is organized automatically. And then based on your prompts, it will complete the rest of the of your prompt, essentially. So if you ask it to do something, it'll continue the pattern. What's great about FemtoGPT is it's a pure Rust implementation, which is you can use it for both inference and training using CPUs and GPUs. They added OpenCL, which is just a sort of like an OpenGL, but OpenCL is like the next. It's a GPU integration library that allows you to access the GPU, and you can do things as simple as matrix multiplications. And this library was open source to us by Kayvon, who has generously given us this code for free. And the cool part is that it's very similar in architecture with Andre's Nano GPT. So if you're fascinated by large language models and would like to understand sort of how these work, you can just take a look at the code. It's minimal code. There is, a good amount of code it requires, right, in order to achieve this, because there's a lot of math involved. Though it's fairly minimal, so you should be able to get the understanding of how it all works. And the great news is that it is relatively fast. I tried it both on CPU and GPU, though even though it's relatively fast on CPU, it works, and it will leverage every CPU core that you have available to you. So if you have a really fast processor, you'll be pretty quick. However, it's way faster on a GPU because the GPU can parallelize these math operations a lot better. So definitely choose the GPU option. We're taking a look at a minimal GPT given to us for free by Kayvon, who's built this open source library for a GPT that you can train your very own model using just your own data. You can bring your own data. Dataset.txt is the file name that this library looks for. What we're gonna do really quick is look over some of the code. Just do a quick code walkthrough so we kind of see what's going on. Just briefly, we see here, this is the main file, the main RS, where everything starts, right? You want to start here at the beginning. And what's great about FemtoGPT and the way Kayvon sort of wrote this for us is there are a whole bunch of reusable aspects. So we've got an optimizer, then we've got the GPT itself, and then a couple of helper functions and even a tokenizer. So we can see initially here in the main, we've got some boilerplate that looks to see if we're running a GPU feature or not GPU feature, right? So then it will be able to target the specific hardware and the functions that are associated with it, right? Because when we are running with a GPU, we need to make sure that we've compiled sort of shader language that the kernel for the GPU will understand. It's sort of like a C-based language that is not Rust. It's C, it's written in C, so you have to write the code in C and then pass that over to the GPU. Then we have here our training state path, which is basically just a state file, right? So what was described to us in the README is this will be the trained model, right, overall. This is where the weights and parameters will live on disk. And then we've got like a nice little RNG here. What's going on there? Okay, so now we're going to read from dataset.txt, which is inside the directory where you run, right? So this is just a static file. That's where you put your data. So if you have a large amount of data, say for example, all of your chat messages, your email responses, you'll be able to take all of the data from that, put it into the dataset.txt file, and then you could format it in a way where it's question answer so that you can create your own dedicated personal you, a digital you, answers any question that anyone's ever asked you, either on a chat message or a text message or social media post or anywhere. You'll be able to put that into the dataset.txt file and then just run it as is. The default will work. You just put your data there and then you run the program. So first things first, it's going to read the data and then it's going to parse out all the different characters that are available to us. I believe I need to look into this to be certain, but I do believe it's a letter by letter tokenizer. So it's not a word by word tokenizer. It's just on a per letter basis. Yeah, okay. So that makes sense. So that helps us have a smaller output size because there's 64 characters, right? And so it's giving us a maximum dictionary size of 64. In that case, like, you know, A to Z, lowercase and uppercase. So that's 26 times 2. And then you get numbers. So there's 0 to 9, which is 10. And then you've got a few symbols in there as well. So this will give us everything we need to get our vocab size. And then we only have 4 layers, so this will be our deep neural network. And then 4 heads from attention perspective. In the GPT model, you have self-attention. This is where you take the entire input string and then you attend every letter to every other letter. And the attention heads is going to be how much attention, how much are we going to attend to that? Because you can do 100% attention where every letter is always, and then you just have a very ginormous attention map. Isn't necessary. You don't need that much attention, though you could. It just costs more compute, right? And you can have more layers and it will cost more compute. There's also a dropout variable here, which I see that we set to 0, which is a training hyperparameter kind of. It allows you to, it allows the model to sort of forget some of the things while it's learning. You don't use dropout during the inference time, just during learning phase. And you can use that to help reduce overfitting, right? Because you want the model to respond organically rather than deterministically. So here are the 2 deterministic parameters. So you see I have a batch size here. How many, in this case, samples are we going to have? And these are going to be letter pairs. So you have 1 letter and then the following letter that's supposed to come afterward, right? So if we have the letter the, TH, that will be 2 letters. So the letter T and then the letter H will be the output, and that will be a batch size of 1. So then we take a combination of 32, which will be 64 total characters. And so one way to help improve the organic nature of this model, you can increase the batch size and you can increase the dropout a little. And this will give you a little more organic with potential to increase error rate. So you can reduce that by increasing the size of the model altogether. And with these parameters in total, you're going to have about 250,000 parameters, which, you know, isn't a lot when you compare it to these very big models, right? These where they have billions of parameters, right? Like Llama 3, that's like an 8 billion parameter model. This is only 250,000, very tiny, very super tiny, but they don't need to be very big because you're training it only on your own specific specialized data. Now we have all the data we need, and then we're going to create our own GPT. Then we pass in all of our parameters, and then we can begin the training process. Oh, this is interesting. Check this out. Okay, so we have a non-static learning rate. It does appear that learning rate is going to be a function, and then based on the number of steps, it's going to reduce the rate of its learning. So you're going to start out with 1 basis point, see here, and then you will drop it down to 100 times less. Well, actually, yeah, no, 100 times less. There's a couple extra zeros there. Then, so you have a warm-up phase, which is kind of interesting. I bet that means that it's going to be a little more. You want it to learn as fast as possible initially, get as much as you can initially, and then you can start decaying, which is a really cool learning rate. I like that. That's kind of a neat way to go about it. Fancy learning rate tuning. Ooh, we've got a dedicated. All right, then we've got another closure here that's being defined. It's going to be called callback. A callback in this case is just sort of a check-in phase. It's like after so many seconds or cycles, it'll call this function, and then you can use it to sort of gauge the current accuracy, how far off it is, and you can print out status. Because it takes a long time to train these models, you don't want to just wait 7 hours, 10 hours, and then see the final output. You want to have phases of check-in to make sure things are going in the right direction. So this is what the callback lets you do here. And then okay, so I see. Okay, so now it's going to serialize the existing model state and save it every check-in phase. So that way it always writes it to disk for every check-in phase. There's probably going to be like hundreds of check-in phases, right? That will occur. And then we jump down to the training loop. Okay, so if it's not GPU, then it will begin the CPU training process for 100,000 cycles. Now, I don't think this is going to be a batch number. I'm pretty sure it's not a batch number. Or sorry, epoch. I don't think it's an epoch. I think it's a batch number. That's what I mean. Not epoch. An epoch in machine learning is a full run through of the entire data set once. That's one epoch. Once you've covered the entire data set. So your dataset.txt file, that'll be one epoch once it's fully covered. This, in my case, I believe is probably just the number of batches or number of trains. So we've got 32 examples in the batch size times 100,000, and that'll be the total number of training iterations. And that's it. That's the end of the file. So one other thing I wanted to check to see here is what does it look like when we see this training the GPU side of things. Under the covers, it's actually pretty neat, well organized, I would say. So we have this functions directory, which is basically all the math functions. The top level directory here, these are all the CPU level functions, so they're very straightforward. So we can add together the gradients, so very simple. You know, I was expecting a plus sign. Oh, here it is. Okay, this is it here. All right, so this is where we are adding together our different parameters. Simple addition. And then if the GPU feature is enabled, then it will be using the GPU add function. And that is tucked away inside of a module folder here, GPU. Let me look at the add. And this, we should see some, yep, here we go. We see some C code that is intended as a shader language for your GPU, mostly because you're going to display cool pixels on the screen. In this case, what we're doing is we just want it for the math aspect, so it can compute the math in parallel across the matrix. So it can take two matrices, for example, and add them together in an instant, right? Because it can parallelize every addition it needs to do. Compare that to a CPU where it has to do like a nested for loop. You can only do one at a time. With a GPU, you can add all these numbers together in an instant, instantaneously. So that's kind of what the shader language looks like here. And we are also using the Rust format here. So we are adding in the different sizes. Okay, so this is probably gonna be like matrix, the vector size. This is pretty nice because I've personally written one of these very similar before. And when you have to pass in the function to the GPU, you need to make sure that everything kind of has a fixed size already defined, because you don't know what it's going to be in the GPU, and you can't change it. So you have to pre-calculate the size every time you pass a matrix or data over to the GPU, so it knows how far to go. Because it compiles on it's a compiler, and it compiles on the GPU, and then you pop it in, and then it can execute quickly, because it's not a dynamic language, it's a compiled language. All right, one last item I wanted to check to see what it looked like from an OpenCL perspective. We have the OpenCL library that we grabbed from Rust, which is the interface to the C library that we can use to directly access the power of the GPU. And this is how it was implemented. It's actually pretty straightforward. This is pretty boilerplate code. What you need is get the context, and then you get the source code, right? So we're passing in the source code, and you also have to identify the device ID, which is usually going to be a number like 0, 1, 2, 3, 4. One thing I did notice about this Femto GPT, it's only going to use one GPU. So if you have multiple GPUs, sort of like these really big AWS servers that have like 8 GPUs or more, you can only use one GPU at a time, which is totally fine for what we're using here. So you just need to make sure not to over purchase. Say if you're gonna run this on an Amazon server, you only really need one GPU when you're doing this. So the context, we've got the context, then we throw in that source code that we saw earlier, and then we just add it to the queue, and then it makes it available for us to execute anytime we want to pass in data over to the GPU to run that kernel. Then the kernel will run, and then it will pass back of reference to the texture memory, and then from there you can copy the data back to the CPU in the system RAM. We're going to compile and build our own ChatGPT from scratch, from zero. We're going to use the Femto GPT open source framework provided to us by Kayvon. We're going to be running it directly on an AWS server, and then we're going to get the output. Essentially, it's really straightforward, really simple. Just go over to GitHub and type in Bimto GPT. Make sure it's by Kayvon K. Then scroll down over here to usage. You'll want to make sure that you have Rust installed. So just run this command and it will install the Rust toolchain, which will allow you to build Rust applications. You'll also need to have OpenCL dev libraries installed on your system. So sudo install OpenCL with the dev packages. That's only though if you want to train with GPU. And you do! You want to train a GPU because it's like 1,000 times faster. Actually, wait, maybe 10,000 times faster. It's ridiculous how much faster it is. So it's absolutely worth it. Then we're going to use the dataset.txt file, which is the default file that's going to be opened for the training purposes. Now, if you have your own data, you can put it into the dataset.txt file. This, the default data is just some language, like Shakespeare language. It's, you know, human English, though if you want, you can put anything you want in there. It could even be your own data, right? So your own chat data. So if you want to build a chat bot, you need to have your name and then the respondent's name. So it would be you and then respondent, you respondent type format, right? So then you can use that data model and format that data model to be able to build a chat bot using the GPT. So it's pretty straightforward. There's a couple other things. The language, there are 65,000 characters as the current dataset size. You can change that if you needed to in the source code. You probably don't need to though. And then you run cargo run release. Now, here's the deal. You need to, if you want GPU support, you have to run a different command. You have to say -- feature GPU. You have to add that onto this. They say it's a 300K parameter model, though I mean, it could be, it might not be. What I saw was around a 250,000 model, right? So it's just about 50K less than this. Yeah, so whatever. But this is way smaller than the billion parameter models that you get with like Llama 3 and Mistral and Google. Those are much bigger. But you don't need a really big one if you're just training it on your own data. So you can see we've got a whole bunch of nonsense here. After training, after just a few hours of training, though it does kind of look like there's something there. But if you keep going and then you increase the parameters, now we're getting something that looks a lot more human, right? And you can continue from there. It gets a little bit better, and then a little bit better, and a little bit better. And then suddenly you've got basically a perfectly working GPT. Okay, so after you've installed the Rust toolchain using that curl command from earlier, then you also install the OpenCL dev libraries. That's it. That's all the dependencies you need to be able to access the GPU on the machine and the Rust, the actual application itself. So I kind of like this because it's a really easy install and it basically works almost everywhere. So you can go forward and then run this command here. You want to make sure to say -- features GPU because it's an optional parameter, but it's the very important one. So here you go, just run this. And I ran it for a while already, for a couple hours. And we can see where it's at running on the Shakespeare data. Now notice that each of these steps, it's elapsing in about 28 milliseconds. That's really fast. The CPU counterpart is around 10 seconds per step. That's way too much. That's insane. So you want to use the GPU option if possible. Now let's pause this here for a second and see. Wow, look at that. And I see the part of the world and I see the world with my phone. Okay, so I've got a full sentence. This is fantastic. It's trained. We can see that our loss rate is pretty low and it's only with 250,000 parameters. So this is remarkably impressive. It basically does what we need. You can go even further. You can turn this into a chat-based model. Right now, this is just a completion model. So what we're going to see is if you type in any part of these words, it's just going to predict that the next phase of words is going to align with whatever is the most likely. So if you want to make a chat-based model where you can talk to yourself or have a copy of yourself, you need to format it in such a way, right? Where you have your name. So for my example, Stephen : and then my whatever I'm saying, and then the person's name, or just say respondent : and then their response. And then you just give a whole bunch of examples of that, put that in the data file, and then now you can use that as a completion chat model, and it will complete exactly copy you and your digital person. You will have your own copy of yourself, and it will run really fast. This model, so fast, it can run anywhere. It can run on your phone, a Raspberry Pi. Because it's written in Rust, it can be deployed anywhere. It can run on an app on your phone. It's amazing. So you can actually leverage this entire repository to train on a GPU and to then deploy the model with the training data file to any device you want. Here is our training dataset file. It's only 2.4 megabytes. That's super tiny. That's smaller than most photographs these days, right? and it will have basically your entire knowledge. Now you're probably going to want to boost that up a bit. You want to grab more data. You can grab all of your emails, all your text messages. Make sure you put them in the right format. You got to say, you know, your name, like Stephen colon, then whatever text it is, and then the respondent's text. And then just make sure to have it in that format. So that way when you're training, you'll be able to do that. You might have to make a few code changes here and there. You also might want to increase the rate of the number of parameters, right? So we look in the main RS file here, and then we see we could increase the number of layers. So we might want to increase that number there. Bigger, more attention, add some dropout. Not that much dropout, like maybe that much dropout, for example. You can increase the batch size. There's a lot of things you can do. And you can go even further and have a lot more tokens. So the output size right now is nice and small at 64,000 tokens. What you could do to accelerate it and to provide even more meaning is to take this letter-based tokenizer and then use a word-based tokenizer. And you can easily swap that in here. So you have to do some Rust code editing to make that work. But you basically have that here as well. And so there are some improvements you can make, though overall you don't have to. You can just literally throw the data that you want into the dataset.txt file, which looks like this. Let's get to our dataset here by dataset. And we have, oh, look at this. Okay, a whole bunch of text. And you see how it's sort of formatted here with the person's name and the respondents. What you're gonna wanna do is, you know, make sure to highlight these and put the right, like put you in versus the respondent in. This is 40,000 lines of text. It's a lot. And then you just run it for a couple hours, a day, however long you want. And now you've got a copy of yourself.